This week we are very excited to have Rares-Darius Buhai as a guest speaker. Rares is a third-year PhD student at TTH Zurich, where he is advised by Professor David Steurer. He is interested in theoretical aspects of computer science and machine learning. Today, he has very kindly agreed to give a talk on his exciting recent work titled Algorithms Approaching the Threshold for Semi-Random Planted-clique. So let's welcome Rares, and over to you.
Thank you very much. So let me open the slides. Okay. I hope you can see.
Yes.
The slides are visible, right? Okay. Okay, so my name is Rai, and today I'm going to present a recent paper called Approaching the Threshold for Semi-Random Planted-clique. And this is joint work with Pravesh Kothari at CMU and with David Steurer, who is my advisor here at ETH. So I'm going to start by talking about the standard planted-clique problem, which is really an average case version of the maximum clique problem. And the entire idea is that you have a random graph in which each edge appears with probability half. And then you put a k-clique in it, and you want to understand if you can recover the k-clique. So I want to depict this as follows. So let's say that I split this graph into this part L, which has k vertices, and the right-hand part v minus s star, which has n minus k vertices. Is everything okay?
Yes.
Okay. And I'm assuming that S star is a k-clique. And then in the planted-clique setting, for the rest, you assume that the edges between S star and V minus S star, as well as the edges in V minus S star in the entire subgraph, are generated randomly. So each of them appears independently with probability 1/2. So the goal in this setting is to try to recover S star. So to recover this k-clique, given that everything is random. And it turns out that how easy or difficult it is to do this depends on how large the planted-clique is, on how large k is. So let's see what is known about this problem.
Just a small question. So the edges between S plus V minus S are also random, right?
Yes, everything outside S star is random. The one between S star and V minus S star, and as well as everything inside the V minus S star.
Right.
Okay. So let's see what is known for this problem. It's actually known that if the size of the planted-clique is less than 2 log n, it's impossible to solve the problem, because in the random part of the graph, with high probability, you'll also have a clique of size 2 log n. So then it's just impossible to distinguish which one is S star and which one is a clique that just appears in the random portion. So it's impossible information theoretically. Again, it's possible information theoretically because the planted-clique will be the unique maximum clique. But this doesn't mean that it's possible efficiently. So let's see about efficient algorithms. So when k is at least root 10 log n, it's known that just taking the k vertices with the highest degree will give you the planted-clique. And this can be improved to any small constant times root 10 with a different algorithm that just takes the adjacency matrix of the graph. It calculates its second eigenvector, and it does some rounding. So the point here is, okay, for k at least some constant times root 10, it's possible to solve this problem in polynomial time. But okay, there's a huge gap between 2 log n and root 10. So what happens there? And it is proved that in this regime, it's actually hard for sum of squares algorithms to find the clique. So sum of squares algorithms are a class of convex programs that are very powerful. Like almost all estimation and average case problems can be captured. Almost all algorithms for these kinds of problems can be captured by sum of squares programs. So the fact that it's hard for polynomial time sum of squares program to solve the problem is taken as evidence that it's really computationally hard. So in general, we wouldn't expect like polynomial time algorithms to exist between 2 log n and root 10. We can still take the positive side here, which is that, okay, for k at least root 10, you can recover the planted-clique. And this kind of thing you cannot do in a worst case graph. Like recovering a root n clique in a worst case graph is still NP hard. It requires exponential time. So then people tried to understand, can you make this planted clique setting a little, can you make it a little closer to the worst case setting? Can you make the setting a bit more adversarial while still being able to something? So one model that tries to do that is the monotone adversary model introduced by Feige and Kilian. And this is a model intermediate between what we study and between the planted clique. And this one looks as follows. So I still have kind of the same picture. You have this S star, which is a K clique. And, you know, it's connected to V minus S star, and you have V minus S star. So what do I assume about these? I assume that just as in the planted clique setting, you generate random edges, and then an adversary can delete any subset of edges in this part, in the part from S star to V minus S star and in V minus S star. And this adversary can do this adaptively, like after seeing what the random edges were generated. So adversary sees first what was generated and then selects what to delete. So this is, okay, this is harder than the standard planted clique in the sense that the adversary could still choose to do nothing. You know, it's at least as hard. But intuitively, deleting edges seems that it should just make it should just be a helpful adversary. It seems that deleting edges should somehow make the problem maybe easier intuitively, because the planted clique S star becomes even more visible if you remove more edges that are irrelevant. But it turns out actually that the previous algorithms for standard planted clique actually fail on this problem because they really do overfit to the fact that the graph is random outside the K clique. So those algorithms can give completely nonsensical results, even on with this helpful kind of adversary. So let's see what is actually known for this model. So all the hardness results from standard planted cliques still apply here unmodified because the adversary could choose to do nothing. So the problem is at least as hard as the standard planted clique. So I just posted like all the results from there. And it turns out that for K at least root n, there is a new algorithm that still works. It's an algorithm given by Feige and Krautgammer, and it's an algorithm based on a semi-definite programming relaxation. So overall, with this monotone adversary, like the landscape, like this line looks exactly the same planted clique. Like it didn't make the problem harder. We can still solve it when K is at least root n. And now comes the model that we actually study, which is we call the is called the semi-random planted clique model, which is also introduced by Feige and Kilian, and which is as follows. So now S star is still a K clique. The edges between S star and V minus S star, so the edges in the cut, are exactly as in the monotone case. So these are randomly generated edges, and then an adversary can delete any subset of them. But about V minus S star, we now assume that this is completely adversarial. It can be absolutely anything, like the adversary first sees the edges in the cut that were generated, and then it can choose V minus S star to be any graph that it make any assumption at all about V minus S star. And this is, as I said, this is the model that we will study. So it's not even clear in this model what actually should be the goal, because it's actually impossible to recover S star. That because V minus S star is adversarial, the adversary could just simulate kind of this generative process inside it. So in V minus S star, the adversary could put that and the K clique, and it could ensure that all the connections, all the cuts between them are random. Then the entire graph that you get as an input looks as having maybe up to n over K cliques, which are completely indistinguishable. Like one of them is S star, but you cannot tell which one is S star. So then the goal that we focus on is actually to recover a list of K cliques that includes S star. And we want this list to have size at most n over K. So as I said before, the adversary could put up to n over K completely indistinguishable K cliques here. So we cannot hope to do better to have a smaller list than n over K. And it turns out that n over K is enough, that we will be able to achieve n over k. So I hope that it's clear what we are trying to do and what the model is. So now I'm gonna say again what is known about this model. So instead of the previous models, it's actually impossible to solve this task for k up to root n, not up to log n. And this is shown by Steinhardt. So it's information theoretically impossible to recover a small list of k cliques that includes the true clique if k is less than root n. And conversely, for k at least root n log n, it's actually possible information theoretically, but not necessarily efficiently. So what is known about polynomial time algorithms? There's an algorithm given by Charikar, Steinhardt, and Valiant, which works when k is at least n to the 2/3 times some. And this is based on a semi-definite programming relaxation. And this is improved by Mackenzie-Matheson to an algorithm that works in time n to the 2/3 without any log factors, also based on an SDP. So overall, what was known up until our paper is that for k at least n to the 2/3, you can solve the problem in polynomial time. And the big open question was what happens between root n and n to the 2/3. This was posed as an open question by Steinhardt and Feige, and they also kind of conjectured that you should probably be able to do it at root n, or at least root n log n, because that's what you can do in the standard planted-clique setting. So what our actual result is that we can approach root n by and achieve a between the time complexity and how close you get to root n. We can show that for k at least n to the 1/2 plus 1 over t, we can solve the problem in this n to the O of t. So as you allow yourself t to be larger and larger, you can get closer and closer to root n. So for example, for t equals 100, you solve this problem in polynomial time, like n to the O of 100, but because this is the exponent is fixed, it's polynomial time. And you solve it for all k that are at least root n times n to the 1 over 100, which is, very close to root n. And like more formally, our result is, our main theorem is the following. For any t a natural number, we give an algorithm that runs in time n to the O of t, such that when k is at least n to the 1/2 plus 1 over t, it outputs with high probability a list of at most n over k, like up to a little of one factor, k cliques, such that it's guaranteed that S star is part of the list. So this is the main result that we achieve in this paper, and for the rest of the talk, I will talk about how we achieve this result. So yeah, let me know if there are any questions so far, and otherwise I will continue.
Can you go back to the previous slide once?
Yes.
So this information theoretical hardness impossibilities for the list decoding setting, is it?
Yes.
But okay, so this MMT and other works also consider the other settings. I like you also give algorithms for that setting, if I'm not wrong, where you're given a random vertex and you want to decode it.
Yes, so that
But
is implied parallel algorithm. If we can get a list such that all the cliques in the list are almost disjoint, and that's something that we get, then we can also solve that setting. So that setting is a setting in which you're given as part of the input a random vertex in S star, and you need to output S star. And what Steinhardt shows that it's hard is that problem, the problem when you're given a random vertex. But that also implies, I mean, our statement is stronger because we give a list, and because that all the cliques in the list have very small intersection, and one of them is exactly S star, it does mean that given a random vertex in S star, you can uniquely identify the thing in the list.
So the impossibility also holds for both the models, and the algorithm also holds for both the models.
Yes. Our algorithm, our model is stronger. I mean, we solve a stronger problem than strictly the problem solved by Steinhardt. And the easier problem is hard. I mean, it implies that the harder problem is still hard. Yeah.
Yeah. Thanks.
Okay. Okay, so to discuss this result, I want to start by discussing how you can find an inefficient algorithm for this problem. And from now on, I'm going to assume that there are no adversarial deletions. So what this means is that the edges between S star and V minus S star are completely random. And it turns out that this is an assumption. Okay, first of all, this is an assumption that's not strictly needed on this slide, but is needed on the later slides. And it's also kind of without loss of generality, because in our specific algorithm, at the end, it's very easy to just plug the assumption back in. So the cut between S star and V minus S star is random from now. The second thing, I want just to emphasize that it's not obvious what an inefficient algorithm is, because you could say, okay, you just output all the k cliques, but this will give you a list of exponential size. It can give you a list of exponential size, because V minus S star could, for example, could be a complete graph, and then there are, exponentially many k cliques in it. So it's not obvious what a good inefficient algorithm is that gives a small list, even if you're allowed for it to run in exponential time. So the main claim that helps us get to something is the following, observed by Steinhardt, that with high probability, S star intersects every other k clique in the graph in at most log n vertices. So if this red blob, for example, is another k clique, the portion of it that lies in S star needs to have size at most log n. And intuitively, this should hold because we are assuming that all the edges between S star and V minus S star are random. But if you have a big clique that crosses between the two sides, that it means that there are really a lot of highly structured connections between the two sides. And we can show that in a random graph, basically, this cannot happen too much. And we will actually prove this claim on the next slide. And the second claim that will help us is the following. When K is at least times L, then any list of K cliques such that each two intersect in at most L vertices has size at most N over K. So intuitively, what this is saying is that if you have many large enough cliques, and each of these cliques are almost disjoint, they have small intersection, then you have too many of them because they would quickly fill up the graph. So you really can have only like kind of what you'd expect, N over K cliques. And this is proved by a simple application of inclusion-exclusion. And these two claims are enough to give us an inefficient algorithm that works actually when K is at least root n log n, so better than our algorithm. And the algorithm is the following. Output all the K cliques that intersect every other K clique in at most log n vertices. So you can clearly, in actual time. So then let's see why this is good. So first of all, note that this outputs S star, because we know that by the first claim, that S star intersects every other K clique in at most log n vertices. So it must be part of the output of the. And now how many things does the algorithm output? Well, we know that K is at least root n log n. Intersection is log n. So by the second claim, the list that it outputs can have size at most O of n over K. So this algorithm actually produces a small list that includes the true clique. And I can also mention that it's even possible to make this algorithm run in quasi-polynomial time, but we are interested in polynomial time. So then let's see the proof of this claim. That S star intersects every other K clique in at most log n vertices. So suppose you have some set of K vertices that's not S star, and suppose that this intersects S star in at least one vertex. We want to understand what's the probability that this thing will be a K clique, this set S. So let's say, for example, there's like this. Like if it is and I ignore here the connections between the left-hand side and the right-hand side. I'm just saying it has some nodes in S star and some nodes in V minus S star. Well, if it is a clique, it means that all the edges between its left-hand side must be present. But all these edges need to be random because they're S star and V minus S star. So the probability, it's really bounded by 2 to the minus size of the intersection times K minus the size of the intersection. because this is how many edges go between the left-hand side and the right-hand side. So for a specific set S, that if we want to know what's the probability that it's a clique, it's this. So now how do we get the general result? Well, by a union bound. So the probability that S star intersects any K clique in more than log n vertices is the following. And I say let L. So I'll just want to go over all the possible sets of size S and count the probability that they are cliques. So let S be the size of the intersection with S star. So we are interested in all the intersections that are larger than log n, so we go from L plus 1. Now, how many sets of size S are there that have intersection S with S star? Well, sets of size K, I mean, with intersection S with S star. Well, there are K choose S ways to choose the vertices in S star, and then minus K choose K minus S ways to choose the vertices outside S star. And for each such set of K vertices, the probability that it's actually a clique is bounded by what I said above. It's bounded by 2 to the minus S times K minus S, where S is the intersection. So if you actually carry out this union bound, you get that this is actually bounded by 2K over N squared, which, this is very, very small. So the probability of a bad event is small. So with high probability, S star intersects every other K clique in at most log n vertices. Okay. Again, feel free to interrupt if you have any questions. If not, let's start to see then how we can go toward an efficient algorithm. So the key structural property that helped us so far is the following. The fact that S star intersects every other K clique in at most L vertices. That's the thing that allowed us to get a small list and everything. It turns out that if we can certify this property in time n to the t, then there is a general machinery based on a sum of squares program, which is a convex program of size n to the t, that gives us an algorithm that runs in time n to the O of t for any k that's at least root n times L, and that gives us basically what we want. That gives us the list with of size n over k. So this general machinery, I'm going to talk in more detail about this in the latter part of the talk. But for now, I want to say that most of this was developed in previous papers that did this mostly in the context of machine learning problems, where if you can certify that some things have small intersections, that you can also get a list. So for example, the paper that I cite here does this in the context of linear regression, when you have a very, very large number of outliers. So you can only hope to output a list of the possible solutions to the linear regression. But for now, I want to focus on this certification task. And as I said, we will discuss about this SOS machinery later. So we are able to extend this machinery and to adapt it to the case of cliques. So what we do in terms of certification is that we manage to certify n to the O of t, that L that is at most n to the 1 over t. So that each intersection is at most n to the 1 over t. So if you plug this L into what I said you get for an algorithm, then you get an algorithm that time n to the O of t, and that works when k is at least root n times n to the 1 over 2t. So it's exactly the guarantee that we want. So then the question is, how do you certify this thing? How do you certify that the true planted clique intersects all the other K cliques in at most L vertices? So first, let me say what this certification means. So for the certification, you can assume that you know what S star is. So in this setting, we know what S star is. And we just need a way to prove to someone efficiently, based on explicit properties of the graph, that S star really intersects every other K clique in at most L vertices. So you could say, okay, but we had a proof of this like 2 slides ago. The issue with that proof is that it doesn't certificate. What that proof said was that basically if the graph is random, then if you look at all the sets of size k, none of them can be, if they intersect S star too much. But to make a certificate out of this, the set would basically be, hey, look at all sets of size k and check if they are cliques and if they intersect too much. And this is obviously an inefficient certificate. So we'll see that there are much more efficient ways by just looking at very few properties of the graph, very explicit properties of the graph, which imply, just looking at these properties implies that all the intersections of S star with any k-clique is small. So let's start seeing how we can get to something like that. So if you look at the cut between S star and V minus S star, so here I'm ignoring the connections S star and V minus S star, just looking at the graph going between them. This is a random k by n minus k bipartite graph. And it's random because the edges between S star and V minus S star are random. So now, if you have a k-clique that intersects S star in L vertices, it actually means that in this cut, you have an L by k minus L biclique. So what do I mean by this? Let's say that this is like a clique, where again, I don't show the connections inside S star and V minus S star. So, it has two vertices in S star, and because it's a clique, all these connections must be present. So I call this structure a 2 by 3 biclique. So if you have a k-clique involved that intersects S star in L vertices, this gives rise to an L by k minus L biclique. So then it suffices to certify that a random k by n minus k bipartite graph does not contain any L by k minus L bicliques, because this automatically implies that you cannot have any k-clique that intersects S star in more than L vertices. So then, for the certification, we're really going to focus on this task. We're going to kind of ignore from now the planted-clique, and we're going to say, can we certify that in a random k by n minus k bipartite graph, you don't have L by k minus L bicliques? And for simplicity, I'm going to talk about k by n bipartite graphs and L by k bicliques. So I'm going to replace n minus k and k minus L by n and k. So let's see how a simple certificate for such a problem could look like, and then I'm going to present our actual certificate. So the example is a spectral certificate. So let B be the adjacency matrix of this random bipartite graph. So you have a k by n bipartite graph, and this gives rise to a k by n adjacency matrix with plus minus 1 entries, where B of I and j is plus 1 if there is an edge between the ith node on the left to the jth node on the right. And minus 1 means that there's no edge. And the certificate that I want to use is that the spectral norm of B is at most root 10. So you can check that for a random bipartite graph, this actually holds with high probability. And what I claim is that this property by itself is enough to say something about bicliques. Without using that the bipartite graph is random in any other way, only this property. So let's see what this actually implies. So suppose we actually have an L by k biclique in this bipartite graph, and let x and y be its indicators. So x indicates which nodes on the left are in the biclique, and y indicates which on the right are in this biclique. So then you can check the following, that x transpose by is equal to lk. And that's because x transpose by really selects and sums over all the edges that are in the biclique. And we know that all these edges, B is going to be plus 1 at these positions because they are in the biclique that we're supposed to exist. And then you can also get a trivial bound, which is x transpose by. This is at most norm of x, norm of y, norm of b. The norm of x is root L and the norm of y is root k, just because they're indicators of this L by k biclique. And the norm of B, by the certificate, it's O of root n. So if you combine these two statements, you actually get that L is at most n over k, which implies that any biclique has size at most n over k by k. So going back to the original problem, this means that any intersection of a k-clique with S star is at most n over k. So we really got something out of this. So let's see what exactly this would mean for an algorithm. If you remember, we get an algorithm from these certificates that works when k is at least root 10 times root L. And in our case, L is n over k. So I get an algorithm that works when k is at least root 10 times root n over k. And if you simplify both sides, this means that k is at least n to the 2/3. So this is very interesting because this matches the previous results. So the previous results definitely do not talk about bicliques in any explicit way or about this sort of spectral certificate. But it seems that we can kind of capture up to log factors what they do by using this spectral certificate.
I have a question here. So
Yes.
if you convert this spectral certificate, you plug it to the SS machine. Does the SDP also match to the SDP that like say MMT or CSV these guys see?
No, it's actually no, it does not match. So it's gonna be a different SDP that achieves the same results. I do not think it is the same because those, at least one of the paper uses a pretty custom SDP in order, especially the one that gets the result without the log factors. For it gets the result with the log factors, I'm not sure actually.
Okay.
But at least for one of those results, they really have a kind of custom SDP, which I really don't think would be the one that you get from this.
Yes.
So now I'm going to our certificate, which is a higher degree and non-spectral certificate. So again, let's say that the adjacents of this bipartite graph, I'm gonna define a new matrix of size k to the t times n, whose rows are indexed by sets of size at most t, and each row is equal to the elemental product rows of B corresponding to that set. So let me show a picture. That B1, B2, and B3, the first three rows of B are the ones I drew here. Then M at the row 1 to 3, for the set 1 to 3, it's really obtained by taking the element-wise product of these three things. So it's still a plus minus 1 vector of length 10. The number of columns is the same. So the certificate that I'm gonna use is that the inner product between any two rows of M is at most root t times n. And you can check that this holds with high probability for random bipartite graphs. What should also be easy to check is that this makes sense for t equals 1. So for t equals 1, you just take two rows of B and you take their inner product. But this is basically just a sum of random plus minus 1 variables, independent variables. So it's known that this has magnitude root n with high probability. And this also extends yet to higher t. So let's see what this implies. Suppose again that you have an L by K biclique, and let X and Y be its indicators. So Y is still the indicator of the vertices on the right-hand side, but X is now an indicator of the sets of size at most t that are part of the biclique. So you take all the sets of this L thing, all its subsets, and X needs to be one at all those subsets. Of course, only the subsets of size at most t, because that's how we define it. So then X transpose My is going to be L to the t times k, roughly. And that's because in the left-hand side of the biclique has L vertices. So how many subsets of size at most t are there in a set of L elements? Well, roughly L to the t. And now, as before, we also want to get an upper bound on this quantity. So let's see how we can do that. So I'm going to start with Cauchy-Schwarz by bounding this by norm of Y times norm of X transpose M. And now I want to expand the second term. And if you check, then this is really equal to summing over all sets of size at most t, S and T, that are in the biclique, and taking the inner product of MS and MT of these two rows, and everything to the 1/2. So you can check if you expand like that to norm that it's this. So now I'm going to separate this in the part where S is equal to T and the part where S is different than T. And I'm going to observe that when S is different than T, sorry, I think there was an issue here. Just look at the orange part now. So when S is different than T, then this inner product by certificate is bounded by root T times N, because that's what we assumed in the certificate. So then overall, what do we get? Well, we get what I wrote here, like the norm of Y is bounded by root K. Now let's see the first sum. For the first sum, how many subsets S of size at most T are in the biclique? Well, L to the T. And what's the norm of MS squared? Well, MS is a row of plus minus 1 values. So its 2 norm squared is n. It's exactly n. And for the second sum, you have the number of pairs is roughly L to the 2t. And you know, the inner product, as I said, is bounded by root t times n. So now we are almost done. I'm gonna do something and then justify it. So let's assume that L to the t is actually smaller than root n. And then the first term in this sum will actually dominate. So then x transpose my is at most root k times root L to the t times n. And if we combine this with the equality that we have, then you have that L to the t is at most n over k. So L is at most n over k to the 1 over t. So just to explain a bit why was it okay to assume here a bound on L to the t? Well, we assumed that, you know, that this biclique is less than root n, but then we showed that even if you have one that's of this size, you can show that there's one even smaller. So basically, if you take k to be like root n to the like 1 plus 1 over t or something like that, then this quantity, I don't know, do you see my cursor, by the way? Or not?
Can you? No, I don't think we see it. Can you try to move it once?
Yes, I was trying to move it. So you do not see. So basically, you can take k to be root n to the 1 plus 1 over t or something like that. Bound that you prove on L to the t is actually smaller than the bound that you assumed, then this turns out to make everything fine. So we get that the size of a biclique is at most n over k to the 1 over t times k. And if you plug this into the algorithm, it actually into, you know, this go through the SOS into an algorithm, then this actually gives an algorithm when k is at least n to the 1/2 plus 1 over t. Plus 1 over t because you need to multiply, you know, by root of n over k to the 1 over t. So this is roughly n to the 1 over t. So this is really the certificate that makes the proof work. And this leads to an algorithm that achieves our stated result. And why? So the last thing to say about this is why is this certificate? Why is this time n to the t? Well, because this matrix M has you know you need to bump the number of rows to k to the t, which is roughly n to the t. Yeah. So let me know if there are any questions about the certificate. If not, then I'm gonna say a bit about the optimality of the certificate. So we have some lower bounds in this paper, but these are only lower. So these are not really lower bounds for the semi-random planted-clique problem. They're really lower bounds for the problem of certifying that a k by n bipartite graph does not contain L by k minus L bicliques. So the first thing we show is that if you just take a basic SDP, if you try to certify this with a basic SDP, a basic SDP cannot certify that L is much smaller than n over k. So basically, it cannot solve the original problem for any k that's smaller than n to the 2/3. So again, this matches the previous results. So a basic SDP cannot go beyond what the previous results do. And the previous results are, in fact, very similar to what a basic SDP would do.
So the basic
yes.
SDP, you mean the lowest theta SDP, the Feige one? What do you mean with?
So I'm not sure if it's exactly, I mean, it's an SDP for this, for finding like a biclique in a random bipartite graph. So it's not one for the clique problem itself. It's the lower bounds only apply to this thing.
I see. So using these biclique certificate, you cannot solve the problem better than n to the power 2/3. That's what you're saying.
Yes, I'm saying that a basic SDP, by using this bipartite certificate, if you try to do this, then it cannot solve the problem for better than n to the 2/3.
Okay.
And we also have some low degree lower bounds, actually. So in this, you try to understand what if your algorithm was allowed, basically, this is intuitively, but if the algorithm was allowed to be just a polynomial in the input, what kind of polynomial would it need to be to even distinguish between a graph that contains a biclique or that does not contain a biclique? And basically, we showed that you need polynomials of degree O of t in order to certify anything non-trivial when k is at least n to the 1/2 plus 1 over t. So, and in general, the time complexity of an algorithm is kind of considered to be related to the degree that you need. So this would kind of suggest that you need time complexity n to the O of t to certify something good for this problem when k is at least n to the 1/2 plus 1 over t. So this somehow suggests that the dependency that we have, like k to the 1/2 plus 1 over t in time n to the t, that it's maybe optimal. So one issue with this is that all of this is for constant t. And in general, low degree lower bounds are considered to be meaningful when you show a lower bound that's greater than log n, where n is a parameter that increases. So overall, we really take this just as some sort of weak evidence that, you know, there's at least something that points out that something does increase with this t. But it does not really imply, there's no consensus, I guess, that this would imply that you really need time complexity n to the t. But it is some form of weak evidence, I would say. Okay, so now I want to talk a bit. So now up to now, I talked about the certificate. I want to talk a bit about how this algorithm actually looks. And how this, you know, the part that I swept under the rug about the general mechanism. So first of all, and you'll see where the certificate comes in. So first of all, I want you to consider this very general quadratic program that just tries to find a clique in a graph. So this is a set of constraints over some W, and I want this W to represent, like, to indicate the clique in the graph. So the three constraints are the following. The first one is that Wi squared is equal to Wi, and this really holds only if Wi is 0 or 1. So the first constraint really says that Wi needs to be binary, so indicator. The second constraint says that the sum of the Wi's is k, so it needs to indicate k vertices. And the third constraint says that whatever it indicates, it needs to be a clique. So the third constraint, what it says is that for any edge that's not in the graph, you cannot have both endpoints being indicated by W, because then this would not be a clique. So if you actually could solve a quadratic program, you know, you could solve the max clique problem, because this finds a clique in an arbitrary graph. So of course, it's hard to solve this program. But it turns out that, you know, taking some sort of relaxation over this, like a sum of squares relaxation, does something useful. The main steps of the algorithms are, and it's fine if for now you don't really understand fully what this means. So the first step is that we compute a degree t pseudo expectation that satisfies A of W and that minimizes the 2 norm of the pseudo expectation applied to W. So I'm going to talk more about what exactly this means on the next slide. For now, I'm just going to say this corresponds basically to computing something like n to the t size relaxation of this quadratic program that I wrote above. And this gives you this object that's called the pseudo expectation that has some properties that depend on this program. The second step is that you use this pseudo expectation that you computed to do some rounding, and this will actually give you already a list of k cliques that includes a star, but it's going to be a potentially very large list, like a list of size n to the t. So in the last step, we just prune this list. And now I'm going to explain a bit, I'm going to go a bit through each of these steps and say more about them. So the first one is, you know, the most tricky in terms of terminology. So what does it mean that, you know, you have the pseudo expectation that satisfies this? So first of all, what does it mean that the pseudo expectation satisfies the constraints? Well, what I want to say is that try to imagine first that you can get a distribution, an actual probability distribution over the solutions to AW, over the solutions to this quadratic program. So again, this is hard, but suppose that you have something like a distribution, then I say that the following would be true. If the constraints A of W somehow imply, if you can prove from them that P of W is greater than 0 for some polynomial W. So if these constraints imply that P of W is 0, this being some property expressed through a polynomial, then it really means that the real expectation of P of W needs to be greater than 0 if you really have a distribution over solutions. And that's because basically every solution needs to have P of W greater than 0. So then if you really have a distribution over them, then the expectation of P of W also needs to be greater than 0. So this holds for actual probability distributions. And now what these pseudo distributions do is the following. Prove. If the fact that A of W implies that the polynomial is not negative, if this is a degree t sum of squares proof, which basically means that you can express this proof through polynomials of degree at most t and their squares of such polynomials. So you can only use in this thing the fact that squares of polynomials of degree at most t need to be positive, and you can also use the constraints in A of W. So if you can prove this thing, then it also implies that the pseudo expectation of P of W is greater than 0. So we still have something similar to before. It's just that now the proof needs to be special in order for the pseudo expectation to satisfy this. So what we actually get from our certificate is a statement of the following kind. So before I parse the statement, I want to say something about the connection of certificates to proofs. So basically what we have is really a sum of squares that the thing I write here is true. So why then did we try to do this thing about certificates? Well, it turns out that whenever you have a sum of squares proof, you also have a certificate of the thing you're proving. And the converse is also in many cases true. So if you find a nice certificate of degree t of something that works in time n to the t of something that you're trying to prove, then it turns out that very often you can turn this into a degree t sum of squares proof. So really here for us, like the hardest thing to do was to find the certificate. And then it was really just technicalities kind of to get to make it a sum of squares proof. So now let's look at the actual statement. So the statement says that, okay, expectation of the sum of y in the clique of wi raised to the t times the sum of j not in the clique wj, that this is bounded by n to the 3. N to the 3 is, I mean, it could just as well be n to the 5. So how should you interpret this? Remember that w is supposed to represent a k-clique, a solution to these constraints. So it's supposed to indicate a k-clique. So suppose that w has at least one element that's not in the clique, which means, okay, let's suppose that it's distinct from the actual true clique. Then the first thing, like the term raised to the t, says that the number of nodes of this clique that intersect S star, if you raise this intersection to the t, this needs to be at most n to the 3, which really means that the intersection of this w with S star, which we denoted L, but before like the intersection of a k-clique with k, this thing can be at most n to the 3 over t. So this polynomial really does encode that any clique, anything that satisfies the constraints, if it's not exactly S star, it needs to have small intersection with S star. And the fact that it's 3 over t, we're not going to care about this, like 1 over t, 3 over t, 6 over t, it's all the same for the purposes of our algorithm. So we get this statement, and I also said that, okay, we try to minimize, we take a pseudo expectation that minimizes this 2 norm. What this really says is that the expectation of W needs to be spread out. So somehow it says that this distribution kind of thing needs to be spread out over the possible solutions to the constraints. So why we need this because otherwise, like the entire pseudo distribution could decide to completely focus on another k-clique, not on S star. But by imposing this constraint, we basically ensure what I wrote here, that if you sum the indicators that are on S star, and you take the expectation, that at least k squared over n, that the mass put on this is at least k squared over n. And actually here, so I'm going to assume that k is at least n to the 1/2 plus 2 over t. Again, the 2 does not matter. And then if you plug this in, you get that, this mass needs to be at least n to the 4 over t. So these two properties, like these last 2 lines about the pseudo expectations, are the only things we will need for the rounding. So let's see now how you do the rounding. So I claim that rounding is this simple thing. Iterate over all subsets of at most t vertices. So Q is a subset of at most t vertices of the graph. Then look at this pseudo expectation of WQ times W. So what is WQ? WQ is just the product of the WIs that are in this set that you selected. And W is an entire vector. So this pseudo expectation is an expectation of a scalar times a vector. So it's a vector. I just say select the largest k entries. Look at the nodes corresponding to those in the graph. And if they form a clique, add it to the list. And I say that you do this for all sets of size at most t of n. I mean, the time complexity of this is n to the t, so it's fine. We can afford to iterate over all these things. So now let's see why this is meaningful. Why does this guarantee that you get S star? And I'm really going to use just the things on the last slide. So the first thing is this statement that I said about small intersections. So I'm not going to repeat what this is. And I'm going to write another statement that looks similar, but in which in the second thing I sum over j in S star, not over j outside S star. So why do I have a lower bound on this? Well, I said before that because we ensure this pseudo distribution is spread out, we have that the sum of the wi's that are in S star is at least n to the 4 over t. And then in this entire term, basically you raise this up to the power, t plus 1 basically, because the term with j in S star is identical to the other term. So then overall, you can show that the pseudo expectation of this entire thing is exactly what you'd expect. You just raise this to the t plus 1, so it's at least 10 to the 4. So you should see that the second term, okay, is much larger than the first term by a factor of n. Like the second equation, the lower bound is much larger than what the bound in the first equation. So I'm going to say that this implies the following, that there exists some Q, some subsets of the vertices that you iterate over that are completely included in S star, such that the expectation of WQ times this second term with sum over j not in S must be much smaller than the expectation of WQ times the j's that are in S star. So why is this true? Think of what would happen if on the equations on the left, you expand the term that's raised to the t. If you expand this term, if you really expand it fully out, you'll get basically n to k to the t or something monomials. Each of the monomials is multiplying at most t terms of the form wi. So it's really like if we expand this sum over wi's to the t, you really get terms of the form wq. And because you know that if you take this term, okay, the first equation says that if you take these terms and multiply by sum of the j not in S, you get something small. And the second equation is that says that if you multiply that by the j in S star, you get something large. So there must be at least some of these monomials for which just the term corresponding to the monomial itself is much smaller in the j not in S compared to the j in S star. So this is what this this is what this is trying to say. Because somehow if this didn't hold, then the lower and upper bound from before couldn't hold. So let's assume that we have this. Then what it really means, it means that, okay, let's look at the term that we said was larger than this term, expectation of WQ times sum in S star. This is approximately double expectation of WQ times all the terms, because we assume that the J not in S star is much smaller. And then we're almost done. Here I'm going to do something slightly sketchy, but I can assure you that it works. Like that, we know that the sum of all of them is k, because we said from the constraints that these w's indicate the k-clique. So then this sum must also be roughly a on the left-hand side if you ignore the WQ. But all the WJs are, are between 0 and 1. So this really means that all the WJs in S star are close to 1. And all the ones not in S star need to be very, very small, much smaller than 1. Because we know that the sum is approximately k. And I'm saying that this thing will hold at least for some of the Q that are included in S star. And therefore, for these things, if you select the k largest entries of this expectation, then you will select exactly the vertices in S star. So I can imagine that maybe some of the things I said here were slightly unclear. Let me know if you have some questions. Or at least does at a high level, like the goal of this was mostly to convey an intuition that detecting the largest k entries is something that that makes sense based on the properties we have.
I don't see any question in the chat. I think at high level it makes sense.
Okay.
You can proceed.
Okay. And now the last step is actually very easy. So the previous step gives you like something like n to the t k-cliques. It can give you something like that. So now we want to prune the list and we do something trivial. We just iterate this as many times as needed. You find 2 cliques in this list. And if they intersect in more than log n vertices, you remove any of them. You can choose whichever of them. And you just iterate this process until you don't have any such cases. I mean, in fact, I think you could even remove both of them, but yeah, not completely clear. So why is this good? Well, this ensures it's clear that we'll never remove S star because we know from the inefficient proof that S star does not in reality intersect any other k-clique in more than log n vertices. So we'll never remove S star. And by the second claim that we had in the inefficient algorithm, we know that if all the things in the output have intersection at most log n, then the entire thing in the output has size at most n over k. So this part, this part is the easiest and ensures what we want. Yeah, so then overall, this is the algorithm. One thing that's interesting and that I want you to notice is that this certificate, we never actually use it explicitly in the algorithm. We use it in the analysis of the algorithm, but somehow the certificate doesn't matter for the algorithm itself. Similar kind of certificate in a completely different way, it's still completely fine. Like the algorithm is agnostic, like the exact same algorithm we work for whatever certificate you prove. Like if you can somehow improve the certificate that we gave, basically you can use still the exact same algorithm that we have, and you will just have proved that you know that it's a better algorithm. So this is a nice feature for a lot of sum of squares algorithms. Yes, so now I just want to say very little about, I'm almost done with the talk. I'll just say very little about one more result that we have. So we can also deal with the case where the probability of the edges between S star and V minus S star are P instead of 1/2. And here the case of interest is when P is larger than 1/2. So when basically when this thing is very dense, because then you would think that it's harder to distinguish. An algorithm that works in time n to the t when k is at least n to the 1/2 plus 1 over t divided by 1 over p to. So this can be pretty large when p is very close to 1. So without saying too much, I'll just say that we improve upon, I think, all the known algorithms when p is not super close to 1. So when p is at most 1 minus n to the minus 0.001, we get an algorithm that's improved. Although improved does not mean optimal or near optimal necessarily. And when p is super close to 1, the reason why our algorithm becomes worse is because we have this dependency on 1 over 1 minus p to the t, so it can really blow up. And I'll just say that the conjectured threshold for general p is root n times p over 1 minus p. So the fact that we have this 1 minus p to the t, shows that we are still conjecture threshold. And as I said, not only us, like every paper, we are in fact better than when p is not too large than most papers. Okay. So then I just want to end with some open questions. There are some open but obvious in our model, like things we haven't really managed to do. Like when the probability is 1/2, like in the standard case, can you actually get to root n log n, something like that in polynomial time, or is it really necessary for the time complexity to increase, arbitrarily as you approach root n? And when p is different than 1/2, okay, can you get something close to the conjectured threshold, like without this 1 minus p to the t? And another open question that I really like is about a similar model, like another semi-random sort of model, which seems harder than this one, which is the following, introduced also by Feige. Suppose that you plant a k-clique at random in a completely arbitrary graph. Can you then find a k-clique, any k-clique in this graph? So notice that if you don't plant this clique at random, then this is really just the problem, because you just have an arbitrary graph, and you could just put the planted clique over a clique that already exists. So there would be no hope to solve it. But now the fact that you plant this clique randomly in this arbitrary graph, could this randomness help you? So this is a problem that seems very interesting, and our techniques currently do not imply something about it. And it's a problem I find really cool. So here I will end my talk. So thank you for listening.
Okay, thanks for a very nice talk. Very cool results. Like now the floor is open for questions. We can take any questions. Okay, I have a few questions which I'd like to ask. So one question is this. So I guess the missing argument is the randomness that you assume, that the reversible deletion process between S and D minus S Does the same argument from Feige Kilian work in your case as well, or do you use a different argument for that?
I think there was a bit of a disconnection. So what did you say about randomness?
Yeah, so you assume that S cross V minus S is perfectly random, no adversarial deletion.
Oh yes, yes.
So
okay,
does
so
this...
why does it work? Why does it also work, or how can you fix that? Okay, so basically I said that we train an SOS program that satisfies this set of constraints A, which is the worst case quadratic program. In those constraints, what you assume about the edges is that for any edge that's not in the graph, that you don't have both endpoints. Well, it turns out that if you have a graph with let's see, with more edges than the true edges, it still satisfies this. So if you ask, if you have a graph in which edges were deleted and you force this pseudo expectation to satisfy this thing for this graph set of things, it will also satisfy the set of constraints for the graph in which you add back all the edges that are deleted. So the fact that you can solve it for the case with added edges means that you can also solve for any case with any less edges. Because somehow, like if you check those constraints, you can see, yeah, exactly what I said. If you satisfy the case with fewer if you can solve it for the case when the edges are exactly half, then it implies that if you satisfy any smaller thing, you also satisfy this bigger thing and the proof goes through. So it's really automatically, like, change anything to the algorithm. The algorithm that I just presented just automatically works.
I see. So that's true in general for other SDPs as well. So, yeah. So the other question that I have is,
if you have something that satisfies like a superset of the constraints, it also satisfies any subset of the constraints, would be a way to put it.
Yeah. Right. So the other question that I have is, so like, do we need SOS to get 10 to the power half? Is there any hope with other SDPs? Like, I don't know whether there are integrality gaps result for the SDPs in CSV and MMT. So, what are your thoughts on that?
Okay, so whether you need this SOS to get our result, or to get the result that's exactly half, like the thing that's better than
maybe just to be 10 to the power 2 by 3, like not even
okay.
get arbitrary.
So yeah, the only way we know how to do it is why do we need SOS with a small degree, with like degree 2, that's just an SDP. So but in our case we need higher degree SOS because our certificate is higher degree. The only way we figured how to get a certificate is by really blowing up this matrix, by making this matrix that has k to the t rows. So that pretty much automatically implies that you'll get an SOS thing of degree t, because you need to work with relations of at most t elements, so you need SOS degree t to even do that. So if you get a certificate, you need to get a certificate that's not high degree, basically.
Right.
As long as you have this certificate that really tensors up rows or columns, I think you will end up with a higher degree thing. And then, okay, it's SOS or a complex enough SDP, but yeah. So if you try to do it with some way that's not SDPs at all, then sure, maybe you can. But I don't know what to say anything about that if you try to do it in a way that doesn't use any SDP. I have no idea then.
Like the basic spectral certificate that you earlier presented, that one probably cannot be improved much, or even that is not known.
I mean, so I don't think it's known. I mean, we have this lower bound that I said, this low degree lower bound, which suggests that to certify this thing about bicliques, maybe you need the degree to go up to t to get to 1/2 plus 1 over t. At the same time, like low degree lower bounds where you prove something for constant degree don't always mean what you mean, so it's not exactly clear. My suspicion would be that for this type of thing, for this type of going through bicliques and certifying it with SOS, my guess would be that you probably need this dependence on T. But it's a guess. We haven't proved anything I haven't written.
Sure. Okay, I guess let's thank the speaker again for the talk. Thanks for the talk. I'll stop the recording and are you free for